In this video, we're going to talk about complex numbers. And take a moment, pause the video, read this Calvin and Hobbes, have a chuckle, and then resume. All right, so a complex number is defined by this a plus bi, where it's got a real part and it's got an imaginary part. So a is just a real number, and this bi tells you that you have a b amount of i's, not the things in your head, but I is represented by the square root of -1. So when you think about a square root, that is the opposite of squaring something. And we know that when I square a number, no matter if it's positive or negative, my result is equal to or greater than 0. And I'll never get a negative, so that seems kind of crazy to me. We're not working in the real number system here completely. There's a real number part, and then there's an imaginary part. So there is this whole other system of numbers and operations called imaginary numbers that come from taking the square root of a negative. And its parent number is the square root of -1. So if we were to think about it graphically, a plus bi, or a complex number, is graphed in the imaginary plane and the real plane together. So it creates this vector of a plus bi, where the imaginary is this b and the real is this a, and it creates this vector to the point, kind of like you were graphing a point in an xy plane, but it creates this vector instead. And something that's really cool is the I cycle. So when you have I to the first power, that is the square root of -1. So what it is, we write I, and if you square that, so the square root of -1 times the square root of -1, remember the radicals cancel, you get -1. So you can take an imaginary number, multiply it by itself, and you get a real number. Crazy. Then if you do I to the third, that gives you -I. That's like saying I squared times I to the first. That's -1 times I, -I. And if I have I to the fourth, which is my favorite one, not that you care, is going to give you 1. That's like I squared times I squared. -1 squared is 1. And if you repeat the cycle, so if you get I to the fifth, that's like I to the fourth times I to the first, which repeats the cycle back up here. So once you count down to 4 and you have whatever left over, you go to that I and it tells you exactly what that's going to be. Again, very cool. So we treat complex numbers just like we do variables and constants, and we can add and subtract them quite easily. So if I have these two examples, you can actually add the real number parts together. So you know what 3 minus 2 is, that's 1. And then I can also add up these guys. So treat I like it's a variable. So if I have 5i and 3i, that makes 8i. And same thing down here. Before I commit some silly buffoonery, I'm actually going to distribute my negative. So I have 6 minus 6, that's 0. And I have 4i minus 3i, so that's plus I, or just I. And if we can add and subtract, we can multiply and divide. Let's multiply here. So I'm going to FOIL this. So I get 10 plus 35i plus 6i plus 21i squared. So I'm going to keep my 10. This guy's going to make 41i, and then I have this 21i squared. Now from before, I know I squared is the same as -1. So this is really minus 21. And if I combine minus 21 and 10, that's -11 plus 41i. And just so you know, we always write it in a plus bi form, where the piece with the imaginary part, or the I, comes second. So something that we've touched on before with real numbers and with radicals, especially in the denominator, is something called a conjugate. Now that takes all the bits and pieces and just changes the sign in between. Now, if I have an a plus bi, the conjugate of that is a minus bi. So let's say that I define that by y. The conjugate is going to be y bar. So if you ever see just that notation without it telling you that it's its conjugate, that's what it means. It's a conjugate. Just so you know graphically, so if I have my regular x here, that's an a plus bi, the conjugate flips over the real, or what we know it as, the x-axis, and creates this over here. Same thing if this is, let's say, y, it's going to flip it over the real or the x-axis, and it's going to give you that conjugate down there. All right, so why is the conjugate important? It comes into play with multiplication. So if I check out this example where I have z is equal to 3 plus 4i, I want to know what z times its conjugate is going to give me. So the first thing I do is I write it out. I get 3 plus 4i times 3 minus 4i. I'm going to FOIL that, and I get something that's going to cancel the middle terms, which is what a conjugate is for. And I'm going to get 9 minus 16 times negative 1, because that's what I squared is. And when all is said and done, I get 25, which, dealing with two complex numbers, you wouldn't think that you would just end up with a nice perfect square that we have here, but it works when I work with conjugates. So there's no need to be afraid of imaginary numbers or complex numbers. That's going to do it for this video. Thanks for watching.